Hi, everybody. Welcome to your notes on magnetism. Please follow along with your guided notes. You can also pause or rewind the video to think, draw, or practice. I am also sitting right here in the room, so please feel free to pause and come to me with any questions or if you want to discuss or have a deeper conversation about anything. So, make sure you're on page 1 of your notes, and there will be different things for you to fill in. Okay, so first off, I want to talk about compasses. Compasses are the very first practical use of a magnet. Compasses are essentially small floating magnets on a needle. Sometimes they're floating on water or oil. They appear to be have been invented independently in China around 1100 and in Europe later in the same century. And they absolutely revolutionized seafaring. Before the introduction of the compass, geographical position and direction at sea were mostly determined by looking at landmarks, things you could see with your eyes, and sometimes looking at the sky and different stars or planets that you could see. In China, sometimes they would sample the mud from the seafloor, analyze the flight paths of birds, or observing the wind and sea debris in sea state, as in Polynesia. They're measuring the distances between stars and planets. The Norse are believed to have used types of sun compasses to locate true north. And maybe on cloudy days, they use different types of crystals. Not exactly sure how this works, but it has something to do with the sun's direct elevation and the polarization of the daylight. And again, astronomical knowledge was huge because that could help you to locate yourself on Earth. However, the invention of compasses made it possible to determine where you were heading when the sky was overcast or foggy or you couldn't see landmarks. And this enabled mariners to navigate safely far away from land, increasing sea trade and contributing to the Age of Discovery, which came about shortly thereafter. So we see magnets absolutely everywhere. We use them to generate electricity, run electric motors, and they help operate appliances like telephones and radios. I mean, obviously you've seen the ones on, your refrigerator door that hold your cupboards closed, but you may not realize they're in your speakers, they're in your headphones, they help your electric toothbrush charge, they make some doorbells functions. They're on credit cards, like the little magnetic strips. They're in some phone or tablet cases. They're in your TVs and your radios. They're used in the speakers and some other components. MRI machines use strong magnets to create detailed images of the body. We use them in particle accelerators, transformers, and obviously the compass, right? So I want to talk a little bit about the concept of dipolarity. Di meaning two and polarity, opposites, right? Magnetite is a magnetic form of iron ore, and it was given its name by a Greek philosopher, Thales, who had obtained samples from a deposit near the town of Magnesia in Asia Minor. Much later, any piece of magnetized rock was called lodestone. Lode meaning coarse, because it was able to give you the direction. So if you were to hang a lodestone from the ceiling, and it was kind of freely swinging, and you twisted and twisted and twisted and released it, it would slowly twist back and forth, finally stopping with its ends in the original position, one pointing north and one pointing south. You could do that as many times as you liked, and consistently. The north pointing end would point north, and the south pointing end would consistently point south. Ended up that we'd start to call the point that points north the north-seeking pole, or the North Pole. And the one that ends up pointing south is called the south-seeking pole, or simply the South Pole. So why does this happen? There must be something causing the lodestone, or in our case, the magnet, to have this attraction, right? So there must be some kind of force originating near the North Pole that pulls or attracts one end, while a force originating somewhere near the South Pole attracts the other end. Now, this is an approximation, basically an average description across the whole Earth, because at different places on the Earth, they actually exhibit slightly different traits, where due north isn't exactly north. For example, if you're in Chicago, and you use a lodestone, it will point north, exactly north, yes? But if you were in New York, it'll point about 15 degrees west of north. And if you're in San Francisco, about 20 degrees east of north. So when Columbus is crossing the Atlantic, this actually really freaked him out because he's like, wow, I think I know where north is based on the stars, but my compass isn't giving me the exact same information. So why does this happen? Don't worry, Columbus, we got you. So today we know why north on the compass may really be northeast or northwest. Inside the Earth, there are many convections and density currents within the Earth's core and mantle, and they make little magnetic fields of varying strength. And when these fields interact, either complementing or opposing each other, their combined effects produces a general magnetic field with poles that don't coincide exactly with our geographic poles. So the place where you are on Earth might not have exactly the same magnetic orientation as the Earth as a whole. So instead, each magnetic pole is about 1,200 miles from its geographic pole. So magnetic pole and geographic pole may not be in the same location. So even though it's not fixed there, the North Magnetic Pole lies in the Canadian North off the coast of Ellesmere Island. You can see a little picture of that here to the left. As the current in the core shifts, the magnetic pole actually drifts northward around the Canadian Arctic at approximately 35 kilometers per year. It's a little bit of a moving target. The South Magnetic Pole is fairly static in its position near the coast of Antarctica. So what happens if you have a magnet or a lodestone and you try separating the north-seeking and the south-seeking parts? You try to slice it right there in the middle. So if a lodestone or another magnet is divided in the middle, two new poles appear, giving each half a pair of opposite poles that mimic the poles in the original magnet. So the north part will stay north and the south part will stay south, but then will appear the opposite on the other side of the magnet. And it doesn't matter how many times you slice it, how small you slice it, every north pole will have one exact south pole. So this demonstrates that a magnetic pole is always paired with the opposite. Thus, every magnet is dipolar, two poles having two opposites. There are no exceptions to this rule that has ever been found, though some theorists have imagined that isolated north and south poles or monopoles can occur somewhere in nature, but the evidence so far has not won general acceptance. It does have something to do with string theory, and if this interests you, stay tuned for a video towards the end of our slideshow. It's not for everybody, but it is really interesting if you want to stick around and see it. So, the law of magnetic poles. So if we have two lodestones or magnets hanging close together, they reveal that there are forces that exist between these two poles. North poles and south poles come together, opposites attract. Two north poles or two south poles avoid contact. These observations lead us to formulate a law called the law of magnetic poles, similar to that governing the interaction between two electric charges, right? Well, remember Paula Abdul, opposites attract. Same thing here. Unlike poles attract, whereas like poles repel. So according to this law then, if I have a compass and it's taking the north-seeking side and it's pointing towards the North Pole, then the North Pole must actually be its opposite, a south-seeking pole. And if the South Pole points south, then the South Pole must actually be a north-seeking pole, a little bit backwards from what you'd expect. I know I always thought, oh, if the north of my magnet points north, then up there must be a North Pole. Wait a minute, but the North Pole is actually a south-seeking pole because it's pulling on north-seeking things. All right, let's watch this little cute video.
A magnet, right? See? So they are repelling each other. North-north. Repel. And north-south?
That was just in case you didn't believe me. Awesome.
A magnet, right?
So, making magnets. In order to make magnets, we will have to magnetize things. So for example, if you had a small needle, it could be magnetized by simply rubbing it against a lodestone or a magnet, and the lodestone or magnet will not lose any of its magnetic strength in the process. That the needle becomes a magnet is proved by its behavior when it's suspended from a string or floated in water. It will now have that north-south attraction and react to other magnets or metals in the way a magnet does. So like the directional indicator on a compass, the needle then assumes a north-south orientation. Magnetizing an object by stroking or touching it with an existing magnet, by actually touching it, is called magnetization by contact. That's one way to magnetize an object. The same needle can be magnetized to a lesser extent simply by placing it close to a magnet. Magnetizing an object by bringing it just in the presence of another magnet without actually touching it is called magnetization by induction. Now we have to be careful because this only works if the materials are right. Materials such as iron can be magnetized because each of its atoms is already a tiny little magnet. An atom with a magnetic pole is called an atom dipole. We learned about these in chemistry. Dipole, the atom actually has two parts to it. Now normally the atomic dipoles within a material receptive to magnetization are oriented kind of like all over the place. They all like point in different directions. But if you bring a magnet into the same close space and they can affect each other, they all line up in the same direction, making it a lot more organized. So question for you, why do you think metal atoms are able to be made into magnets? What do we know about metallic atoms, how they bond and what their valence electrons are like? That would mean that they'd be great candidates to turn into magnets. Well, it has something to do with their unpaired or valence electrons. So we will talk about that a little more in this video.
Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 21. It's on the magnetic dipole moment, which is the torque that material experiences when you put it in a magnetic field. And so if you add an object to a magnetic field and it's not affected, then it doesn't have this magnetic dipole moment. And so let's say we take a bar magnet like this. Is it magnetized? Well, a quick way to figure that out is to use a compass. And so a compass is essentially a small floating magnet on a needle. And so if we put this next to the bar magnet, you can see that the south side of the compass is facing the north side of the magnet, and vice versa down here on the other side of the magnet. So we would say it's definitely magnetized. And it's the magnetic dipole moment inside the bar magnet that's causing it to be magnetized. But let's say I want to break this magnet, and I just crack it in half. Have I destroyed the magnet? Well, we'd test it in the same way. We'd use compasses again at either side, and you can see that they line up. In this case, the north side of this magnet is facing the south side of the smaller magnet. And so now we've essentially created two dipoles. And if you break it in half again, we have two smaller magnets, and you can keep breaking it and breaking it and breaking it. And what you'll find is you'll just make smaller and smaller and smaller magnets. And so there's something intrinsic in the magnet itself that's causing it to be magnetized, and that's the magnetic dipole moment. And so matter that shows a magnetic behavior has this property called the magnetic dipole moment. And so it could be at the level of domains, they're really small parts of a magnet. They can be up to about the size of a millimeter. But if we break down those, they're built up of atoms, and atoms themselves are made up of electrons. And the spin of those electrons gives them a magnetic dipole moment as well. And so all of these levels of dipoles is creating the overall effect of a magnet. And so what is magnetism? Well, in a permanent magnet or an induced magnet, what we're doing is lining up those dipoles, and now the whole object has a dipole as well, a north and a south. And so to understand what a dipole is, it simply means two charges. And so if we were to look at an electric dipole, right here we have a positive charge and a negative charge, and then we have electric fields that form around the outside of it. So this is an electric dipole. Watch how this diagram changes as I move it to a magnetized dipole, and you'll see that it really didn't change at all. Now we've got a north and a south, and instead of having an electric field, we have a magnetic field. And so what is a magnetic dipole? It's simply a dipole, two charges, but those are magnetized. And so if we were to look at a bar magnet like this, it has a north and a south side. But what really is creating it are these domains inside the magnet itself. And so iron, for example, that's not magnetized, what we would find is inside those domains, the dipoles are there, but they're facing in every other direction. And so if I were to change this and make it a permanent magnet, watch what happens to those domains is they all essentially line up. And so it's the domains that must be causing the magnetism. Well, it's not. It could be the atoms as well. So if we look at the atoms themselves, those are made up of charges, and so those can have dipoles. And even if we get to the level of electrons, electrons, because of their spin, are magnetized as well. And so at all levels through in the magnet, we can see these dipoles, and those are contributing to the overall behavior of the magnet itself. And so what is a permanent magnet? It's essentially material that can permanently create these magnetic fields. And so if you ever add it to another magnetic field, it'll experience a torque or a moment based on those magnetic dipoles. And so does all material on our planet have the ability to be magnetized? No, it's based on the internal atomic and molecular structure. But if I were to take paper clips, for example, put them next to a permanent magnet, they could be an induced magnet. In other words, all those domains are starting to line up, and then you would have a paper clip that is an induced magnet. And so it's only a few of the elements on the periodic table that can be lined up like this, being ferromagnetic. So it could be iron, copper, nickel. And then we have these rare earth metals like a neodymium magnet that we have right here, and it has this ferrofluid over the surface of it. You can almost see those magnetic fields coming out of that magnet. And so did you learn that a magnet is created through these magnetic dipole moments that occur at all different levels inside the structure of the magnet? I hope so, and I hope that was helpful.
All right. So, now that we know how to magnetize things, we should definitely talk about demagnetizing the things, which obviously means the opposite of magnetizing. So just as magnetic properties can be acquired, they can also be lost. An existing magnet can be demagnetized under several conditions, including heat, rough handling, and improper storage. So these are all things we're not going to do to the magnets that are around the room. So like poles have a weakening effect on each other. So when magnets are put away, they should be stacked in pairs, north to south and south to north. It often helps to keep a piece of soft iron, a keeper, across the poles at each end of the pairs. So here we have a good illustration of what something looked like when it's magnetized. All the little domains inside are neatly oriented, demagnetized. It's a hot mess in there. So let's talk about some types of magnets. In order to know how easily a material is magnetized, you simply have to look at how strongly it responds to a magnet. So no material is entirely unresponsive. Even water is responsive. We're going to take a little video look at that in a second. Every material is either attracted or repelled, although the responses may be so feeble as to be undetectable under ordinary circumstances. Now, at room temperature, the only materials that react significantly to the presence of a magnet are a few metals and their alloys. We have iron and steel are strongly attracted. Cobalt, nickel, gadolinium, and dysprosium are attracted less strongly. But watch what happens to water. It's crazy.
Hey Magnet fans! This video is kind of a follow-up to Brainiac 75's awesome video about whether powerful magnets will attract to the iron in our blood. If you haven't seen it, you should definitely go check that out first. In his video, a small cup of blood was placed on a piece of styrofoam floating in a bucket of water. It's a great trick to show the weak diamagnetic forces from a strong magnet to the small cup of blood. The force is very tiny, but it does repel the little cup of blood just a tiny bit. While we were watching it, it occurred to us that the effect might not have anything to do with how hemoglobin reacts in a magnetic field. After all, blood's about 50% water. No matter how much that tiny amount of iron in red blood cells might react, you might still see the diamagnetic repelling action because a strong neodymium magnet repels water. There are a lot more water molecules in his cup of blood than iron molecules. Anyway, this short video shows the same kind of diamagnetic repulsion between a magnet and a cup of water.
I really love something that this video, I really like something that this video creator did, which was to change the container of the water, just in case we weren't absolutely sure what effect the glass cup or the plastic lid would have on the magnetism of the situation. We noticed that, yeah, you know what, really, the container didn't have much variation effect, and really we can start to think about how water is even repelled by a very strong magnet. All right. So let's talk about temporary and permanent magnets. So although pure iron is one of the easiest materials to magnetize, it easily demagnetizes as well. It goes both ways. So iron magnets and other easily demagnetized magnets are therefore classified as temporary magnets. They don't get magnetized altogether, yes? If a magnet must be capable of both rapidly gaining and rapidly losing magnetization, this is the kind of magnet we want. And the best material for it is a permalloy, an alloy of nickel and iron in a 3-to-1 ratio. When it is turned north-south, a bar of permalloy sufficiently magnetizes in the Earth's magnetic field to attract iron filings, but instantly drops them when it's turned east-west. Now, magnets that retain their magnetization are classified as permanent magnets. And permanent magnets are made of alnico, which I think is so cute because it's an alloy of aluminum, nickel, cobalt, and iron. So if you were ever worried about remembering it, remember alnico, and that'll tell you what it's an alloy of in various proportions. Another permanent magnet contains rare earth metal compounds of cobalt. Now, I want to talk a little bit about Coulomb's law of natural force. Here on the left, we have a picture of Coulomb's balance. And Coulomb adapted this balance to the left to study magnetic force. And we know that we've talked about Coulomb with respect to his laws for charge. And I think you're going to see something really cool coming up. He discovered that magnetic force and electric force are governed by similar laws. To be specific, the magnetic force diminishes with the square of the distance between the two magnetic poles and increases with the product of their respective strengths. This should sound very familiar with respect to the law of electric force, where we had the denominator being the square of the distance between the charges and the numerator was a coefficient with the two strengths of the charges multiplied together. So take a look. On the left, we have Coulomb's law of magnetic force. So the magnetic force is equal to the constant of proportionality divided by P1 and P2, which are the charge of the two poles, multiplied together in the numerator. And in the denominator, we have the distance between the poles. And again, we're thinking about these like unrealistically as monopoles, but basically the length between the two ends of the magnet. And if we remember Coulomb's law of electric force at the right, you'll see this looks really, really similar. Yeah? So let's talk a little bit about the magnetic field. Since one magnetic pole exerts a force on another at a distance, we may again suppose that the influence is mediated by a force field, right? Remember we were talking a little bit about the idea of like gravity creating a field of influence and a charge creating a field of influence around it. Magnets also, if they're going to produce a force at a distance, there has to be something that covers that distance, and we think about that as a field. The first pole alters the surrounding space in such a way that the space itself impresses a force on the second pole. The altered space is said to contain a magnetic field. And again, we think about fields as forces acting over a distance. So if we're going to be mapping a magnetic field, you might have seen a picture like this before. I know that that Campbell's going to be like, ew, it's gross. It looks like, okay, I know what it looks like, but that's not what we have here. Yes. Here we have a picture of a magnet. And we've sprinkled on some iron filings. You guys are going to get a chance to do this on your own as well. But on diagrams or drawings, scientists often use kind of like these imaginary lines called lines of flux to show the effect, basically to give you a picture of what the force looks like, the direction that it's kind of exerting its influence. And it's very similar to the lines that we drew when we were discussing electric charge. A magnetic field is not confined to just the lines that we draw, just like an electric field is not confined to the lines we draw. And the magnetic field also exists between the lines of flux that we draw. So please pause the video here, head to station 1, and you can complete the instructions there. All right, I hope that was interesting. And now we're gonna talk a little bit about the way that you draw the lines of magnetic flux. So the first rule and requirement for drawing the lines of flux or mapping lines of flux is number 1, the direction of field strength acting on the isolated north pole is tangent to a line of flux at every point. Now, if you took my geometry class, you know that tangent means touching at one point. So if the line of flux is curved, as we see it here, you might be able to see my little cursor is curved. If the solid blue line here is curved, and that's the direction of the line of flux, basically at any point, if you draw a line that touches that point at one point, you have the line of tangency, and that's going to be the direction of the force. So if I'm coming up this way, that will be the direction of the force. Or if I'm coming at it from this angle, that would be the direction of the force. Or that would be the direction of the force. Or that would be the direction of the force. Pew! That's tangent. Yes? So each line of flux shows the path that would be taken by an isolated north pole if it were placed somewhere along this line and restricted to gradual motion, right? It's not going to be changing over time. It's just going to go meow. Number 2, lines of flux must be drawn as closed loops. Closed loops because they're infinite. They keep going and going, yes? There's no starting or ending point. So if we look over here at figure 23.5 to the right, you can see an example of that. You can notice that every line of flux associated with a bar magnet comes from the north and goes around and ends up at the south pole of the magnet. An isolated north pole placed on a line of flux would, if it were able to pass through the body of the magnet, travel indefinitely around in a loop marked by that path. So it's not like it goes in and kind of like dies in there. It then comes back in the other direction, yes? And makes a big old loop. So when the two unlike poles of two opposite magnets are positioned together, you can see that on the right-hand side, like poles, lines of flux bridge the gap between the magnet. When the like poles of two magnets, I spoke incorrectly. Let's look at the left-hand side first, the unlike poles. When unlike poles of the two magnets are positioned close together, again, it comes out of the north and goes to the south, so it kind of bridges the gap in between the two magnets, coming from the north, heading into the south here. And when magnets of like poles, here we have two north poles, are positioned close together, the loops appear to be repelled. It might come out of the north, but it's not going to go into the north. It's going to go away from the north, so they get pulled away from each other in both directions. Pew, pew. See that there? Number 3, the lines of flux are more concentrated where the magnetic field is stronger. We might remember this from electric field strength as well. So the lines of flux are drawn perpendicular to the surface of the magnet. So if you're looking at the surface of the magnet right here, it comes straight out. If you're looking at the surface of the magnet over here, it comes straight out, perpendicular to the side of the magnet. And the number of lines must be proportional to the average field strength upon that surface. That means the more lines, the stronger the field strength, and that should be something that's predictable that we can see. Now, if we're talking about the field strength of a magnetic field, another word for that the field strength at a particular point in the field is called magnetic induction. Now you might be thinking, wait, I've heard that word before. That's charging something by bringing something close to something else. Well, that makes sense. The stronger the magnetic field, the more likely you'll have magnetic induction. This magnetic induction is symbolized by a B, and it's commonly measured in Teslas, who we will talk about. Not today. So when you do it right, if you're drawing your field lines right, you can make a lot of really cool field maps depending on your magnet. You can see this cool looking bar magnet graph over here. Again, you'll notice that the field lines are perpendicular to the surface they originate from. They come from the north. They go to the south. We're making these lovely closed loops. And again, you could anticipate that the direction of the field strength would be kind of coming right off those loops, tangent to the line. All right, let's talk about permeability. Permeability is the ability for something to go through something else. So permeability is the extent to which a material absorbs and concentrates these lines of flux. And it's related to how permeability, or how strong it is magnetized by a magnetic field. Permeability is symbolized by mu, that little Greek letter mu. Iron and the other materials used to make magnets have the greatest tendency to absorb lines of flux. They have high permeability. So I'd like you to test this out. Pause the video here and head to station 2, and you're going to be able to complete the the little lab station over there. Please enjoy. All right, now if you were paying close attention to the video that we watched, magnetic moment might be something that you noticed the guy in the video mentioned. And so that's what we're going to talk about next. Why should magnetic force have a strong effect on some materials like iron, but hardly any effect on other materials like the glass that water was held in, or plastic? Well, we have a couple of theories for this. Some are more useful than others, but let's talk about 2, right? One is the electron magnets theory. So magnetism in an atom can be attributed to the sum of the electron spins on their own axes. So when we were in chemistry, we did talk a little bit about this, the idea that electrons not only have a negative charge, but also they spin. Not physically spin, because electrons are complicated, but we can think of it as a spin. And as electrons spin, so does the electron's charge. And since the constant circular motion of this charge kind of acts like a current flowing through a loop, an electron is a spin magnet because it rotates on its own axis, and the extremities of the spin axis are magnetic poles. So we'll learn this a little bit more when we talk about electromagnetism, but stick with me at this point. If you spin something and it creates a current, we get a little baby magnet out of it, yeah? So however, since an electron is a combination of particles and energy waves, and waves do not spin, please hear this, scientists believe that the electron may not spin at all, but exhibit a magnetic moment as though it did spin. Again, electrons, super small and super complicated. We're still working it out. So this magnetic moment is still described as magnetic spin, but only with a metaphorical understanding. It doesn't really spin. So the movement of electrons orbiting the atom, remember we have the nucleus with the neutrons and the protons tightly packed in the center, and the electrons live in their orbits around the nucleus. So the movement of these electrons orbiting the atom's nucleus also creates a magnetic field. Because their orbit produces a magnetic field, the electrons also produce magnetic moments as orbital magnets. So not just spin magnets, but orbital magnets. Now this effect is really small and actually results in the repulsion of either magnetic pole. It's always repulsive. So, most or all of the electrons within a given atom are paired with another electron of opposite spin. So if they have opposite spins and they're producing like these baby currents in opposite directions, what'll happen is they will have what's called an anti-parallel orientation, and they'll cancel each other out because they always produce opposite fields. Their magnetic fields from orbiting, not spinning, do not cancel each other out because electrons always orbit in the same direction. So really, if we think about it, we only have the properties as an orbital magnet, not a spin magnet. So, an unpaired electron, because it doesn't have something else to cancel out its spin, it doesn't get canceled out. So when an atom containing unpaired electrons is exposed to external magnet, the electron rotates so as to bring its spin axis into alignment with the magnetic flux. What happens then? The result is an attraction between the external magnet and the unpaired electron. And this attraction is greater than the repulsion due to the electron's orbital motion. And this leads us to the idea of domain theory. So, even apart from the influence of these fields, however, there are these small regions containing billions or trillions of atoms with electrons that are not oriented at random. And since unpaired electrons within the same atom have parallel spins, their combined effect creates an atomic dipole. And this is called the domain theory. So, for the domain theory, groups of atoms with unpaired electrons turn one by one until they align with the magnetic field. So you can see on the left the unaligned domains, and that material is not magnetic. If that same material got aligned so that the little domains, the little groups of atoms within the material all point in an organized way, that can usually happen when an external magnetic field is introduced. The domains will align with the field and begin to force neighboring domains to align. And if the field is strong enough, the spin axes of all the unpaired electrons will point in the same direction. And this condition is called saturation. So, just to say a little bit more about this, if this feels a little overwhelming, you can just take it with a grain of salt. But through an exchange reaction predicted by quantum mechanics, neighboring atomic dipoles tend to orient themselves in the same direction, and this orientation spreads to other atoms to form a domain. So that's how domains are formed, aligning magnetic poles. A piece of unmagnetized iron is divided into 1 millimeter thick groups of small domains, and each domain is about 0.1 millimeter thick, so really, really tiny. One domain is separated from another domain by about 100 atoms. You can think, atoms super small, this is very, very small amount. So rather than being a solid domain wall, these 100 atoms actually represent the minimum space required to notice a definite change in the domain's magnetic orientation. So let's have a little chat about the Curie point. So we talked a little bit about how magnets can be demagnetized by heat, right? So an iron magnet can be demagnetized by heat. Basically what happens is the heat shakes the atom dipoles out of their strict parallel alignment that we saw in the previous slide. You see those aligned domains, so neat, so tidy. But remember, when we heat things up, they start moving around faster and in a more disorganized way. They get shaken out of their parallel alignments, causing the reemergence of these separate domains. The temperature that is high enough to disturb the domains of a substance completely is called the Curie point. And above the temperature of 770 degrees Celsius for iron, the material changes from strongly attracted to weakly attracted because we shook up all those domains. Let's watch this video and you'll see it in action.
Hi gang! Here's a fun short science video demonstrating the Curie temperature, or Curie point, using this neat little heat engine. This black thing at the end of this copper wire is a piece of nickel metal. It's attracted to this area by these powerful magnets. But that puts it in the candle flame. Once the nickel gets hot enough, it's no longer attracted to the magnets and falls away, where it can cool off. Once it's cooled enough, it's attracted back to the magnets, and the whole thing repeats. How does it work? Like all materials, a piece of nickel metal is made up of atoms. The atoms it's made of act as tiny magnets, mostly due to electron spin, but we'll just think of the whole atoms as magnets. Another term for these tiny magnets is dipoles. In nickel, these tiny dipoles are grouped into domains. Each domain is a group of tiny magnets, all pointing in the same direction. But notice that the magnets of different domains point in different directions. That's why nickel doesn't normally act like a magnet. But when we put it in the magnetic field of a permanent magnet, the atoms in the domains now point in the same direction, lining up with the magnetic field. Now the nickel behaves like a magnet as a whole, and is attracted to our permanent magnet. We call a material that behaves like this a ferromagnetic material. But that pulls it into the candle flame, that heats up the atoms in the nickel. What that means is that the atoms start to move around randomly, but they still stay lined up with the magnetic field. And at a certain temperature, called the Curie temperature, the tiny magnets all of a sudden all point in different directions. They aren't even grouped into domains anymore, and so it no longer acts like a magnet and falls away. Until it cools again, and the tiny magnets line up with the magnetic field again. Here's how I made it. To start with, I needed some nickel. I could have used other materials instead, like iron, but iron has a Curie temperature of 770 Celsius, or 1418 Fahrenheit. For nickel, the Curie temperature is only 358 Celsius, or 676 Fahrenheit, much quicker to heat up. Often people use nickel wire for this, but I didn't have any. Luckily, Canadian quarters made between 1968 and 1999 are 99.9% nickel. And looking at a roll of them I had, I found one from 1974. I started by drilling some holes in it. A whole quarter would have taken too long to heat up and then cool down, so I cut out a small piece. I then attached some wire to it. For the powerful magnets, I had these two neodymium magnets, taken from a computer hard drive. A quick test shows that the nickel is attracted to the magnets. But when I heat it above the Curie temperature, it's no longer attracted, until it cools down and is attracted again. I hung the wire from a screw and did some testing to figure out rough spacing for things. Next, I assembled this metal and wood structure out of scraps. To hold the screw in place, I put some more magnets, one on either side of this piece of aluminum, and used them to hold the screw in place. I then did something similar with the hard drive magnets. The nice thing about this setup is that it's all easily adjustable. I lit the candle, put it in place, and started adjusting things. And in no time at all, I got it working. Well, thanks for watching. See my YouTube channel, rimstar.org, for more fun science videos like this. That includes one on how a prism works to form a rainbow of colors,
Right,
one all
thank
about magnetic
you.
fields with very...
Very
I
cool,
did-
right? So let's talk a little bit about the different kinds of materials we could classify based on their structure. So we have diamagnetic materials. Diamagnetic materials are materials as a whole that are repelled by a magnet. So orbital magnets are repelled by external magnets. And some examples of this are copper, mercury, sodium, chloride, gold, lead, and noble gases. So Faraday's discovered that some materials are repelled by a magnet as he worked with bismuth, the most diamagnetic material at room temperature. So if you want to remember this, D is for doesn't, does not attract. Yes, diamagnetic materials are repelled by an external magnet. And again, I don't know if anybody recalls drawing the orbitals in chemistry, but remember, those little arrows represent electrons that are spinning in opposite directions. And because all of them are paired, they all cancel, their spins cancel each other out. So we're just dealing with the orbital magnets, and the orbital magnets always have a repulsion. So we also have paramagnetic. So if a material has one or more unpaired electrons for each atom, the material is attracted to an external magnet. So paramagnetic has only one unpaired electron per atom, and it is weakly attracted to a magnet. So examples of this would be aluminum, oxygen, and wood. So you can think pair like it pairs together. Yeah, it kind of is attracted, again, weakly attracted, but that's because it has only one unpaired electron per atom. So again, it will be attracted to a magnetic field. Now we have a special class called ferromagnetic materials. These guys are strongly attracted to a magnet because it has two or more unpaired electrons per atom. Some examples would be iron, the leading ferromagnetic material, and it has 4 unpaired electrons in its third shell, accounting for the unusual magnetic properties of it. Now, cobalt and nickel are also similarly structured, so they would also be ferromagnetic. You can think fer like ferociously strong. And let's pause the video here for today, and we will pick up with electromagnets on our next video. Thank you for listening.